Well, the determinant of a squared matrix is a very special number that you can compute. It will appear many times in the following lectures and will be crucial to evaluate whether or not a matrix has an inverse. There is a very special formula for this calculation, for this determinant of a matrix, but rather than going and give you that formula, let's first see some properties of the determinant and then use those properties to arrive at that formula. So there are 10 properties that we are going to focus on. So the first property is that the determinant of the identity matrix I is equal to 1. Let's take a simple example. The identity 1, 0, 0, 1, well, the determinant of this matrix, of this squared 2 by 2 matrix, is the number that has the name like this. So this is the number, the determinant of the identity matrix 2 by 2. Well, as the first rule says, this determinant is equal to 1. Now, if the identity is 3 by 3, it's again the number 1, and so on. It does not matter the dimension of the matrix. It could be 100 by 100. Well, the determinant of that identity is still just 1. So this is the first fact about this very special number that we can get for squared matrices. The second rule tells us, well, if I exchange rows on the matrix, I have to change the sign. So for example, if I have this matrix and I exchange the rows, giving me, for example, 0, 1, 1, 0, so I just exchange the first and the second row, well, the determinant of this matrix, of the 0, 1, 1, 0, well, I have to change the sign as the rule 2 says. So if this is 1, this must be minus 1. So I just flip the sign. The same thing if it is the identity 3 by 3. You just exchange two rows. Well, the number is still 1, but you have to put a minus there, okay? Because you have to flip the sign. If on the other hand, you just flip two rows, the one time and then the second time. Well, this time, well, you have to put a minus sign for the first switch and then another minus sign for the second, but the minus cancel. So even permutations of rows, an even number of permutation of rows, well, the determinant is still 1, so it does not change the determinant. This is very important. An odd number of permutations will always get us with a minus sign, while an even number of permutations gives us a plus sign. Now, rule number 3. The rule number 3 essentially says that the determinant is linear, but it's linear row-wise. Let's see two examples. If I multiply the first row by a number, I can pull this number out. That's it. So I pull the number out and I get 3 times this number, the determinant of A, B, C, D. If on the other hand, the number 3 is on the second row, well, it's linear also on the second row. I have to pull out this number and gets us this. So this is the first rule. Remember, linearity means I can pull the number out. On the second example of linearity, well, if I add on the first row, I can just do the distributive. So it's the determinant of the A, B, C, D, and then 5, 5, C, D. Let's take, for example, what would be the case if the determinant was linear in both rows simultaneously. So let's imagine for a moment that scenario. In that scenario, I have the determinant of this matrix, everything is fine here. And now, if it's row-wise linear, but on the 2, well, I could write something like this plus something like that. But you see, this is false. This is not true. This is what it means to be row-wise linear on both. But the determinant is only linear in each row, one at a time. As I'm showing here, or here, I can pull the 3, or I can just do distributive like this. Now the fourth rule is as follows. If a matrix has two rows which are exactly the same, then the determinant is equal to 0. Let's see an example. I have here a matrix, I have the determinant of that matrix, and if I flip the two last rows, so if L3 is switched with L2, well, I get this, but notice the matrices are still the same, because the rows are the same. So the determinant of this must be the determinant after switching the two rows. So this number is equal to that number. However, you must remember the second rule. The second rule says that if I flip two rows, I have to put a minus sign into it. This is what you see here. The determinant before the flip, the determinant after the flip, and the minus sign required by the second rule. So, I have now two equations here. Two equations for this number. How am I going to solve this system of equations here? So this number, see it like x. This is like x is equal to x, and the second equation tells us x is equal to minus x. What must be x? Can you see? Just think about it. Well, the only possible solution is that x is equal to 0. 0. Just like I said here, the determinant is 0 as long as there are two equal rows. Now let's see the next rule. So any linear combination of rows, well, the determinant stays the same. This is quite special. It will be very useful in solving exercises, this rule. Here is an example. So I have here a matrix A, B, C, D, on which I just subtracted from row 2 the row 1 times 2. So this times 2, well, it's here. This times 2, well, it shows up here. Can you see? Well, what I claim is that the determinant of this matrix is exactly the determinant of A, B, C, D. But why is that? Well, let's just use the rules. Remember, the determinant is row-wise linear, so I can write this as the summation A, B, C, D, the first part here, and then AB minus 2A minus 2D here. Can you see? But notice, it's again row-wise linear, so I can pull out the minus 2 like you see downstairs. So this number stays the same, minus 2 times that. But notice, two rows are equal, AB, AB. So this must be 0, right? So in conclusion, we arrive at the determinant of AB, CD, just like we'd said previously. So linear combination of the rows, so if I subtract from row 2 twice the row 1, I get this, and the determinant of this matrix is the same as the determinant of the original matrix. Very important rule. The reason why it's so important, by the way, is that many times it's useful. It's useful if you have a complicated the matrix with many non-zero entries. It's useful to use this elimination procedure to eliminate to put as many zeros into the matrix as possible. This is crucial. Not only makes it easy to compute the determinant later on, well, the determinant stays the same, because again, the elimination process is essentially combining two rows. Well, but the determinants always stay the same. Notice, by the way, that there are three things that we did in elimination, by the way. One of them was a linear combination of rows, like we see here. Another one was multiplying a row by a number. Well, if equation multiply a row by a number, well, the equation stays the same. This is another thing that we did. And we also, during the elimination process, we sometimes flip rows. These three things, when done to a system of equations, well, the system stays the same. Why? Remember, well, if I do these three things to a system of equations, well, the equations stay equivalent. So the solution of the system is still the same. So again, three rules that we used during the elimination procedure to solve the system of equations, well, only one of those three things leave the determinant the same, which is, well, like we see here, the linear combination of rows. If I flip two rows, the determinant changes, it gets a minus sign. If I multiply a row by a number, the determinant changes because the determinant is row-wise linear. So this is very important to remember. Only linear combinations of rows, which is by itself already very useful, leave the determinant exactly the same. Now, let's move to the other rules. Continuing with our determinant rules, the sixth rule is a row of zeros in our matrix means that the determinant is 0. Well, let's give a justification for that. I have here a matrix AB 0, 0, so it has a row of zeros. But writing this is the same thing as writing this. AB 0 times C, C is whatever number we like, and 0 times D. D is whatever number, because any number multiplied by 0 is again 0, so nothing changes from year to year. But now it's very important, because 0 and 0 appear here, and I can pull out this 0, like you see on the last step, and we have 0 times the determinant of A, B, C, D. It's a number. But 0 times as a number is always 0. The seventh rule is very special, because it only applies to upper triangular matrices. Upper triangular means only the upper triangle is non-zero. The other is zeros. In this case, well, the determinant is just the multiplication of the elements on the diagonal. Let's just give a small intuitive idea of why this happens. Just imagine that we have our matrix, and I can do all this linear combination of rows. Well, these zeros could have appeared here because of that linear combination. I was able to use this pivot to eliminate this entry and this entry, so get zeros, and use this pivot to eliminate that one. But now I can go further and try to introduce zeros on the upper triangular part. Using linear combinations, eventually I would get 3, 0, 0, 0, 2, 0, and 0, 0, 1, just by using elimination. But if I arrive at this stage, now it's easy to use the other rules, because remember, the determinant is row-wise linear, so I can pull the 3 first, then pull the 2 second, and the 1 last. So I get something like this: 3, 1, 0, 0, 0, 2, 0, 0, 0, 1. I just pull the 3 out, which is the same thing, and now I pull the 2, so 2 times 3, 1, 0, 0, 0, 1, 0, 0, 0, 1. Well, but this is the same thing as that, right? There is no number here to pull out, it's just 1. So if I pull out 1, 1 still stays the same. So you see the idea, the reasoning? So this is why the other rule was so important. The linear combinations rule is so important, because if I simplify enough to have upper triangular matrix, well, I just look at the diagonal. I can forget about everything, every other contribution. Now let's see the last rules. So the eighth rule: dependent rows mean determinant is equal to 0. Here's the reasoning for that. I find here a matrix with the first row here. I put it pink color for its entries, the second row in blue, and finally the last row is a summation of the first and the second, whatever numbers they are. Now, if I have a matrix with this property, then I can use the other rules, in particular the linear combination rule, to eliminate that row. For example, L3, the new third row, is the old third row minus the first minus the second. But because the third row is a summation of both, well, we get zeros. But we already have seen that a row of zeros on our matrix means the determinant of that matrix is 0. So this is 0 immediate. Which is very useful to use this rule in combination with the others. Now let's see the ninth rule. The ninth rule, I'm not going to give a justification, it's just let's use this as a fact of life. So if you have a product of two matrices, well, the determinant of that matrix, the product matrix, well, it's just the determinant of the first times the determinant of the second. So the multiplication of this number with that number. Very useful rule again. And finally, the 10th rule. Well, if you transpose the matrix A, well, the determinant of that matrix is the same as the original one. This means, again, if two columns are dependent on each other, the determinant is 0, just like this here. This is specific for rows, but if the determinant of A transpose is equal to A, well, you can say the same thing that you say here. Instead of rows, you can mean columns. Just switch. So that's it. This is all the rules that we need to compute any determinant. Now, let's use those rules and apply it with two examples. First, a 2x2 matrix, and then a 3x3 matrix. And in the process, let's try to derive the generic formula to compute the determinant.